Ah, even Niranjan is not there. Yeah. So I'm really early then for standards. What course is this? Do you guys know? Like cybernetics. Stuff.
Good morning, Dr. Sajesh.
Today I'm going to control the camera. We'll see if it's any better.
Last week it was good actually.
Huh?
Last time it was really good. I was able to see everything.
I'll try to do better.
Thank you.
It's easy to see from outside and say that you'll do better and then you fail.
Maybe you can keep it a little smaller. Like
You want it zoomed out?
zoom out, yeah, because then you can cover big content in the board.
Oh, then
Yeah.
you can see better overall bird's eye view. Is this better?
Little, can you make it a little bigger? Yeah, that should be, yeah, that works. Yeah. So you don't have to change it every time then.
Let's see. Let's change something. Sorry. Yeah. Mhm. Thanks. Yeah, let's try this again. It okay?
It looks good, yeah.
Bottom it will cut. So, not like. Is this readable?
Not as good as the beginning part. Should be the camera angle.
Is this readable everywhere?
Yeah, yeah.
I will work with two boards. Let's see. I think Abdullah said he's not well. You guys said thermodynamics? Oh, you guys don't know, you guys guessed, right? That's it. Maybe statistical, maybe it's like this. No problem. Have you guys started the homework? How is it? The one that is due today, which was posted very late last week. Have you guys started? So it's going okay? Reasonable? Yeah. Okay, so. Let's put on. Is this readable actually? Because I write smaller sometimes on this.
Yeah, it is readable that area, yeah.
Yeah, try to get the procedure for that we are going through now. Green's function is a technique. And if you get the technique, it becomes easier. Of course, it is eventually just solving differential equations, but there are these boundary conditions where you look for coefficients. And even though it might seem like these equations are simpler here because these are all exponentials, the same idea goes through with more complicated special functions. Just exponentials needs to be replaced with the appropriate special functions that come in later on. I'll do one explicit example after the Thanksgiving break that should help conveying the point that this is actually what is going on, or you might get a bigger picture of what this method is for. We got the Green's function last time for the forced harmonic oscillator. And it is good idea to put it back into the solution and see how the solution looks like, where that fits in. And I also want to show the fact that there is an arbitrariness in the Green's function itself. You don't have to have the same Green's function giving a solution to a differential equation. So even though it might be overkilling the problem, but to emphasize on the idea of Green's function, I really want to do this spend more time on it. So we're saying forced harmonic oscillator. Readable? Niranjan, readable? No.
It's that clear.
Why do people write so small? Is this better?
Yeah, yeah.
I'll forget to write. We had our differential equation to be plus omega naught squared x of t equal to a of t plus boundary conditions. We said x naught will be x. Let's have some simple boundary conditions of this equal to 0 plus velocity equal to 0. Velocity, remember, is the derivative of position with respect to time. Oh, I think we'll be on this. Given a problem like this, we immediately say, oh, that's not what I want to solve. I'm going to instead solve a different equation, which apparently has more variables. Say you solve for the Green's function, e comma t prime is equal to delta of t prime. So that's a Green's function equation. And the idea is that if you can solve for the Green's function, the solution x of t itself is some alpha times exponential I omega naught t. Remember, these are the homogeneous differential equation. There is a homogeneous part which is fixed by the boundary condition or initial conditions plus you have minus infinity plus infinity t prime and g t comma. Did we use capital G earlier? Did we use small g or capital G? I keep switching in my notes. Yes, small, yeah. And a of t prime. And and we realized that the Green's function has boundary conditions, right? So, or continuity conditions, let's say it's the continuity conditions on G. That is derivative with respect to time. Time. Evaluate this at t prime plus delta equal to t prime minus delta. That's equal to -1. So that's your first boundary condition. Or sorry, first continuity condition. So we differentiate between boundary conditions and continuity conditions. Continuity conditions are derived from the equation itself. Boundary conditions are given in the problem. They are configuration dependent. And this is G of the comma T prime evaluated at E equal to G prime plus delta minus delta. That means this is continuous. This is discontinuous. Derivative is having a step discontinuity. If you based on this, we can we derive our Green's function to be G of T comma T prime, even before solving for the coefficients, or let's say I solve for, no, even before solving for the coefficients, I said this was equal to, what should I do? What did we do? Remind me? Yeah, I think what we said is that the Green's function has a homogeneous solution, because if I set P not equal to T prime, then the right hand side goes to 0. But yeah, maybe stress on that, right? So minus P of P comma T prime is equal to 0 for T less than T prime, and it's also equal to 0 for T prime less than. Oh, what happened? And we said that implies that I can write two solutions. So it is e raised to I omega naught t plus b e raised to I omega naught t, and this is c e raised to I omega naught t plus b times e raised to minus I omega naught. That's your solution for t less than t prime less than t. And the continuity conditions is really used to patch up these solutions. So these are two solutions on the right and left. So this is your P, there is a P prime there on the left side of P prime. That's the solution on the right side of the P prime. That is another solution, and we patch things up. And the solution we got, I won't do that again. If I use my continuity conditions in this, we said that we get the solution P of T comma T prime is equal to A times e raised to I omega naught t plus B times e raised to minus omega naught t. And help me, or maybe I should look up if my notations match. Oh, yeah, minus I over omega. The function t greater than t prime. Enough. Right. That was our solution. You guys agree? Yeah. Okay. And we also did one more thing, is that we actually substituted this into this Green's function equation itself and verified that you indeed get delta function. So we know that this solution is indeed correct. This was never a problem because this is a homogeneous solution, right? That will be equal to 0. So that has to be true. And this we verified that it gives a delta function. Let's do the following. So here, if you notice, there is this arbitrariness, right? I solved for C and D here. I could have solved for A and B. Who stopped me? Right? I could have solved for A and B. I could have solved for A and C or B and D. In fact, there are infinite number of combinations you can have. I can have half of A, half of T, there are various things you can do. And you will get different solutions here. Linear combination wise very similar, but they will be literally different solutions. And they will all give you delta functions, but then you see that, so Green's function is not unique. So how can the solutions be unique? So let's at least do this for two different cases, and in your homework, you do emphasize on one of the solutions. So let's see. Okay, so we have the Green's function, substitute this in here, and your solution becomes x of t is equal to alpha e raised to I omega naught t plus beta times e raised to minus I omega naught t. And I have all this input, right? So let me first do this. So I have minus infinity. Notice, yeah, let me do this slowly. 2 steps plus infinity dt, and that is a times e dt prime, e raised to I. I'm getting smaller, I don't space. Is it readable still?
Yes.
Plus beta e raised to minus I omega naught t, right? T, not t prime. And times a of t primes. Still, this is equal to plus or minus 1 over omega naught dt prime okay, that should be, that's, I basically just substituted it back in there. Notice this comes out of the integral. This is a heat dependent quantity. Whatever is remaining, whatever it is, it's a constant because it's an integral in t prime. It cannot depend on anything. So this is equal to alpha plus, if you want, minus infinity to plus infinity to t prime, a of t prime, a times a of t prime, a times a and a b, that is confusing. Same letters I used. Okay. I'm not going to change this, but there are two a's being used for different purposes. A here is a constant in the differentiate, or that arbitrariness in the, or an integral constant if you want, and a of t prime is the forcing nature of this. This is times exponential I omega naught t plus beta plus b times dt prime a of t prime. Times exponential of minus I omega naught t and minus I over omega naught minus infinity to plus infinity dt prime. Notice a step function. Whenever you get a step function, this is 0 when t is greater than t prime. This is 1. No, I said it the opposite, right? This is 1 when t is greater than t prime. Right. So this is 1 if t is greater than t prime, and this is equal to 0 if t is less than t prime. That means this integral limit t prime divides this integral into two pieces, 0 to t and t to infinity. It survives only when t prime is less than t. So that means t has to be on the upper end. I'm not going to write this step function anymore. So instead, I say this is an upper limit in there. And this is sine of omega naught t minus t prime times a of t prime. And you immediately see that these are constants. If I have my initial condition, now all this is maybe I can absorb this. Let's say this is alpha prime e raised to I omega naught t plus beta prime. Alpha prime is square bracketed, it doesn't matter. Whatever that is, minus 1 over omega naught and minus infinity to t prime and a of t prime. Of course, for a specific problem, I need the specific a of t prime, but let's keep it as it is. That's my position. I need the velocity also because I want to put in the boundary condition very quickly. So velocity at time t is equal to the differentiation. That's I omega naught alpha prime minus I omega naught. Here, okay. The minus b prime e raised to minus I naught t. And now when I take the derivative, I have a derivative with t. So I have to take wherever I see a derivative, I have to take a derivative. There are two places where there is a derivative. There is a t here, and there is a t there. When I take the differentiation on an integral limit, what is the derivative structure? So maybe efficient. So d by dx of integral, let's say 0 to x dx prime of f of x prime. What is that equal to? This is 0. This is 0. Oh no, that's f of x minus f of x minus f of 0. Try again. X minus x. The f of 0 will be 0. F of 0 will be 0. That's this one. Yes, that's correct. Right. So remember, differentiation and integral are inverses of each other. How do you prove this? How would you prove this? Suppose you don't believe this. Whenever there is a differentiation problem, you use ab initio point, right? F of x plus delta x. So this is the derivative of this function, right? So let me go up. Okay. Space there, I guess. Let me. So if you take derivative of this quantity, you say f of x plus delta x, right? So 0 of x plus delta x, let's say delta x, times dx prime f of x prime. Is that clear what I'm doing? Derivative of g of x is g of x plus delta x minus of g of x divided by delta x, and then take the limit delta x tends to 0, right? That's how you take the derivative. That's how Newton would have done it. So this is equal to, but now this whole thing is g, right? So this is g of x plus delta x. Right. So I have to subtract this g of x minus g of x prime. So, right. So that's minus of integral of 0 to x dx prime f of x prime divided by delta x, and the limit delta x tends to 0. How is the numerator look like? This is an integral going from 0 to x, and here there is an integral going from 0 to x, and then x plus delta x. Right? I can break that integral into two. So this is the same as x to x plus delta x. Notice it gets away from the 0. You guys are struggling with what happens at 0. That's all gone. It's only the wherever x sits around that integral happens. So this is x to x plus delta x, p of x prime, f of x prime, divided by delta x. If you were to think of this as an integral of a function, wherever this x is, this is a small area element of this is x plus delta. In the limit x plus delta x to x plus delta x, that strip area is 0. Right? Technically, that area element is 0, but you're dividing it out by the width of delta, width of that strip. So when you divide that out, it is just the length that survives, and length is f of x. So you say that this is nothing but in the limit visible. So that's nothing but delta x times f of x divided by delta x. That cancellation is very crucial, and it is f of x itself that survives. Right? So that's a geometric or simple way of deriving, but that's true. There's no approximation of anything in there. Now I have to do the same differentiation here.
Or you can change the limits from
In this case? Here?
Yeah.
This is 0 to x, correct?
If you change the limits, like.
Or if you say this one was x1, right? Same thing. Because it is x1, x above. Like this whole area doesn't matter, right? This is not contributing to it. It is just that strip. Because we're subtracting out the whole area minus this whole area. So it will never, the lower limit doesn't come into picture at all. It could be minus infinity to there and still. This also plays a role again. Yeah, I don't think that is what contributes to the Kramer-Stronach rule. Kramer-Stronach rule has, Kramer-Stronach has to do with causality. Causality is very important in physics, and when you do that, you will see that there is an arbitrariness in the choice of the function before 0. But I suddenly was thinking maybe that is related to this, but I don't think so. Overthinking it, yeah. But this is just maybe this is, what is this called? Fundamental theorem of calculus. Fundamental theorem is a total derivative. Yeah, this is the fundamental theorem of calculus. Yeah. Yeah, so it doesn't depend on the lower limit. That's I think that was it. Okay. So coming back to okay. So because of this differentiation, I have to hit this t and the t that is appearing inside the integral. So first hit this. When I hit here, it's only the value of the function at t notice value of whatever I'm integrating on, replace the integral parameter with the upper limit. So I'm integrating on t prime. I have to replace it with t. But when I do that, that's sine of the function. Sine of 0 is 0. So I get 0. All that is not contributing, but not necessarily in another Green's function that I'm going to do very soon. So that's 0 when I'm hitting the upper limit. And when I really hit the sine omega t here, that's cosine omega naught t, and omega naught comes in, and that kills coefficient there. That's p prime, cosine omega naught t minus p prime, and a of 1. Again, notice very general. I'm not really saying what is my forcing. Usually in a forced harmonic oscillator, you will say this is the forcing of the kind sine omega t. But we can do that. I think that is your homework problem where your forcing function is sine omega t. Then you can actually do this in different way. Okay, so now we have x of t and v of t. So that's your two solutions, or your solution in and the derivative of the solution. And let's put in the boundary conditions, and I'm going to do that right here, filling space. X of t is 0, so x of 0 is equal to 0. That's our initial condition, and that is equal to, at t equal to 0, I have alpha prime plus beta prime, and at t equal to 0, my whole integral will go from minus infinity to 0 here, and sine of omega naught t. So there's a minus sign that comes out if I can do all that in one go. That's omega naught minus infinity to 0 dt prime, and sine of omega naught t prime times a t prime. I really cannot do this integral without specifying my a of t prime, but this is my solution nevertheless, and I have two conditions, a alpha prime plus beta prime, which will let me determine, or I have two equations which will let me determine alpha prime and beta prime. Velocity is also 0 at time t equal to 0, so that's equal to I omega naught alpha prime minus I omega naught beta prime. And now I take the limit again from minus infinity to t. And I think that stays minus equals. T of t prime. Two equations, I can solve for this. I can put my I on this side. Let's basically solve for it. So, yeah, let me keep these things intact. Move on the right side, which I haven't yet set yet. So we have alpha prime plus beta prime is equal to 1 over omega naught minus infinity to 0, and beta prime minus e prime, and I have alpha prime minus beta prime is equal to divided out
The first one is minus.
minus.
Yeah.
Write it this way. So divide it out by 8 and now it's plus. Okay. Let's- Prime here, 2 prime. We can solve for alpha prime and beta prime, solve it. This you can just add, right? So the alpha prime is equal to. Okay, so when I add and then I divide by 2. So I have minus 1 over omega naught minus infinity to 0. And find prime I am actually adding, right? So this plus cosine omega naught. One of them has an I. That. Yeah. So and this will be minus I suppose then if I'm adding. Correctly. Okay. Fine. Two inputs in my mind. Is this correct? Father helps sometimes. Right. So with adding, so now it's plus. Yeah. But sine and cosine are exponentials, right? So this is exponential of I omega naught p prime. Oh, that might be this form. Uses equal to minus 1 over 2 omega naught prime exponential I omega naught p prime minus exponential omega p prime over 2 times I minus by 2I to the p prime. So one of them cancels clearly. And one of them adds. This cancels up. The other one adds, that gives you minus 2 right omega and plus 1 over 2 I omega naught. If I do the same thing for beta prime, maybe faster, maybe not. Beta prime, subtract them, right? So it is minus 1 over 2 omega naught, and when you subtract them, you basically add and minus infinity 0 into prime sine omega naught p prime plus the sine omega naught p prime over by the of p prime. When you add your only difference, I suppose, here is that this has become a plus if this is a first, the second term cancels out. And second term cancels out, so it is exponential. I mean, e with a positive sign, so this is minus, and I still comes out, so it's 2i omega is plus. Prime exponential plus I omega t prime times e prime. Remember again, if your forcing function was provided to you, these are nothing but half Fourier functions. These are half angle Fourier functions, not completely Fourier functions, but half angle Fourier functions. So that's why you will often see that when you're working with harmonic oscillator, you work in Fourier series, but we are not specifying A, but for our purposes, alpha prime and beta prime are constants determined by initial conditions, and we have a solution at this point. And let me write this down for there. Yeah, so you allow me. And I want to do the same thing again for a different way of proceeding. Okay, so the first one of the solutions we have is x of t equals to alpha prime and beta prime. Keep it all intact and keep this alpha prime, not substituting it there. But yeah, this can be processed again, I should say, but let's keep it as it is. Minus or minus. Prime. My alpha prime is equal to 1. This is all from the component quantity and the minus sign. Yeah, do this alpha prime star. Maybe. But if I take this star, I get that. Take this term from this not the way. Probably correct. Okay, so that's our summary of the solutions. First, you solve for Green's function, put it back, then substitute in your initial condition. But as I said, all this could have been, if I had given this problem to two of you guys independently. At this stage, when you had the Green's function, we went ahead and solved for C and D. Someone else might have come and solved it for any other of the two. Like 5 different, if I had given this an exam, no reference material at all, just randomly you would have said, oh, I want to solve for A and C, or B and D, or A and like keep C and D and solve for A and D. So let's do one of them. I will do it for A and C, so that it mixes up. If I were to solve, if I were to get rid of A and B and have C and D, then the only difference will be that this will become a step function, right? There was a step function here, it will actually become the opposite. This is called the retarded. Yeah, maybe I should point out the names here. This is called the retarded Green's function. So this is called the retarded Green's function, which is the most popular retarded Green's function. What did retarded mean? In English, there are two meanings. Retarded. Yeah, actually, probably both have the same meaning. Retarded usually in the standard language, it will be you're slow. Is that correct? What's the meaning of retarded? You're slow, I suppose, and probably that's or here at least the essence is that here it is a past that is affecting you. So the past is pulling you down. So probably you're getting slower. That might be the idea. I don't know where the origin of the word is. The main point is that it is a past, right? P prime or the value at P is getting affected by all the past. The past is affecting you. You might think that that is very causal, so that is how it should be. But here, let me now show that suppose I had started with the opposite. I had done C and D, solve for C and D. I started by saying maybe I'll do A and C, but now while I'm doing the nomenclature, I'm going to solve for C and D and get the solution to be related to the future. So all the future will get affected. At the Green's function level, remember physics is not completely dictated by the Green's function all the time. So I can have the future affecting the Green's function, but the solution cannot depend on the future, right? Solution is causal. Solution has to be determined by the past. But this will all work out in such a way that it is actually the past that is going to help. So let's see, let's go through this in a certain extent detail. Now that we know the technique, we might be able to do this quickly. So let's go back and go back and do all this again, right? So we have till here. I can do this. Solve for, there was this continuity conditions we had, take the derivative. Also, I'm going to do all this in one stroke. So okay. Remember the continuity conditions are right here. So G at T prime plus delta, T prime minus delta. Right, so G of T prime plus delta, T prime minus T prime minus delta T prime is equal to 0. And derivative of G T prime plus delta T prime minus derivative of G T prime minus delta T prime is equal to -1. Right? That was our. No, there was something else. -1 over omega naught, I think. No, this was just just minus. Sorry? Derivative is with respect to dt. That's just a symbolic way of writing. So that was the same equation since I was just writing it. Same continuity conditions. So I'm going to do that in my head to a certain extent so that I save some space. So I'm doing this is t less than t prime less than t. So t prime t plus delta will be here, second one, right? So it is c minus a, c minus a times exponential of I omega naught t prime and plus d minus b times exponential of minus omega naught t prime, that's equal to 0. That's one thing. When I take the derivative, it brings out an I omega naught in each one of them. I'll put that to the right altogether, and I have C minus a again. E raised to I omega naught t prime, and this one will have a minus. And divided by I omega naught, so it is minus 1 over I omega. This is the same equations you had the previous lecture, right? I'm just rewriting until this stage, it is the same. At this point, I said, what did I do? I said I'm going to solve for C and A, but let's do the opposite. Or let me write down the solution here. I think maybe I can write this. Yeah, C minus A, right? So if you guys have the solution, can you tell me C minus, probably I know. This times this, 1, and this times this is again 1. That comes out 0. Is there something wrong here?
Minus 1 over 2.
Huh? Oh yeah, minus 1 minus, so minus 2, right? Yeah. So minus 2, and then I put this, I'm solving C minus A, so it is minus 1 over 2I omega naught. And is this start?
Yeah.
Okay. And D minus B will be equal to do the same thing here, so it is plus e raised to I omega naught t prime over E I omega naught. So this is what we had earlier. And when I was solving, I said I want to solve for C and D. So that I can replace this, but this time let me solve for A and B. So I have my Green's function to be equal to. So the Green's function, I'm going to solve for A and B. So A is equal to C plus exponential of minus I omega naught t prime over t omega naught and e raised to I omega naught t, plus B is equal to D minus e raised to I omega naught t prime over t I omega. Really have to have a memory of what we did last time, because here I kept A and B last time and C and D was replaced. So I'm doing the opposite. So C is kept intact. C and D is kept intact. Does that ring a bell?
Yes.
Oh, sorry. Sorry. Forgot.
We need to move the camera.
Yeah.
Yeah, thanks.
Yeah, okay. Again, what did we do last time? We had the same, we reached this stage. We solved for C minus A, we got these equations. And now I have the choice of replacing C and D's or A and B, or for that matter, any combination. I can do various things here. I solved for C and D last time and wrote the solution in terms of A and B. These A and B were there. Now I'm doing the opposite. I just picked, let's solve for A and B. So I have C and D intact. So C e raised to I omega naught t stays. D e raised to minus I omega naught t stays. And whatever is remaining is surviving for t less than t prime. So let's write that down. And it is a sine function, I suppose. So plus. So plus 1 over omega naught times sine omega naught t minus t prime or 0. T less than t prime less than t. If I want it to survive only on the top expression and not at the bottom, then I say it is a step function for t prime greater than t. Right? So I write this as first step function t prime greater than t over omega naught. And forget this. Too many things at the same time. Which is slightly different from last time. Where is it different? It is the step function that it is different from. And you would say that, oh, that should change everything because now it is the future that is getting affected. At this point, everyone will start doubting this. Oh, how can a physical system depend on the future? Here, it is the future. All the terms in the future is affected. T is the observer. T prime is the source. And all the sources from the future are coming in. But what we are going to show is that after you put this back in the solution, initial conditions will reset itself in such a way that the final solution will be exactly the same. It will come out to be the past that is affecting. At the Green's function level, you can have future contributing. So it might seem that this is not causal, but at the end, the physical problem is related to your position and velocity, not with the Green's function, at least the way we have constructed it. That's not going to bother us. Again, one should realize that I have mentioned this very in passing, that Green's function really becomes physical at some quantum field theoretical level. And then these becomes really an issue that, oh, there is a future affecting your present, and how do you deal with that? And you might have heard of solutions where particles going in the backward direction is equivalent to a negative energy particle. So those are all interpretations coming out of this in a quantum field theoretical level. Here, we just pretend that this is our Green's function, and we want to try to understand how this does relate to our solution that we have got earlier. So now let's begin with this, and let's again solve for our alpha prime and beta prime. Right? That's your Green's function. And let me again go back and get my solution. Let me convince you that this is indeed the same, and there is no future affecting the present. Okay, so that's my Green's function. Go back. And now we go at x. So x of t is equal to alpha e raised to I omega t plus beta e raised to minus I omega t plus minus infinity. There is a plus 1 over omega naught, and my integral is going from minus infinity plus infinity to t prime step function that t prime is greater than and sine omega naught like earlier. Step function basically puts a limit on the integral. So this becomes plus 1 over omega naught. And since t prime has to be greater than t, the integral limit has to be greater than t. So it is t the bottom limit. That has changed your solution a bit from earlier. Earlier it was minus infinity to t, so notice already that sources in the future are contributing, right? This is a statement that this is not causal. If this was the only solution, this is not causal. Observation type, sources, this is the source, right? Forcing function. All the forcing function that happened after I looked at it is actually contributing. That seems very odd. That should not happen. But we will see that it will all work around, cooperate itself in such a way that it'll be okay. Okay. Again, we need velocity, right? If I want to solve for alpha and beta, so I need velocity. This time I have to hit this and this. What is the integral? We did the derivative of 0 to x. What is x to 0? What will that be equal to? Negative f of x, actually. So because it will be x plus delta x to, when you subtract it, it is the lower limit. So this will be negative of f of x. Very good. Quiz, right? I showed that earlier. I showed this for upper limit, show this for the lower limit, and make that a small quiz. So we have this negative number, alpha e raised to I omega t plus beta e raised to minus I omega t. When I take the derivative, whatever it is evaluated at x. So when I evaluate t prime at x, that goes away. So it says 0 there. Does it contribute? And when I hit here with t, it is a plus cosine omega t. It's t plus infinity t prime. Oh, 10 minutes to show that whatever is on the right side of the board is exactly the same. Let's put our initial conditions. 0 x of 0 is equal to 0 is equal to alpha plus beta, and we have t equal to 0, that brings in a minus 1 over omega naught t infinity prime omega naught prime.
What happened to the I omega naught?
Yeah, what happened to I omega naught? I forgot. Thank you. I will struggle otherwise later. Even dimensional, right? So I omega naught, and it just stays there, right? Minus. Thank you. And did I miss anything here? Here I took care of it, right? Yeah, I guess that. Dimensional. Yeah, thank you. So this is. And that's here. Yeah, thank you. So do the same thing here. I omega, not alpha, but I'm going to divide this, right? So it is alpha minus beta, dividing by I omega naught. So it is the derivative of cosine is sine minus. No, I'm not taking it, but what I'm doing. Better. Takes off. Put this as alpha and beta. So this becomes like here maybe alpha plus beta is equal to 1 over omega naught T infinity T prime. And add them, alpha is equal to them. Add them. So it is 1 over 2 omega naught T infinity T prime. Of the I here, right? So minus goes away and minus is minus 2 cancels out. So each infinity and the T prime exponential beta is the same thing I have just subtract. So when I subtract, this will change signs and it'll be plus.
Same thing.
Huh?
Alpha star.
Oh, yeah, is it the same? Probably. Probably, but let's just check it here. So, yeah, probably you're right, most probably that's what it's gonna be. So it's this plus this, so it's 1 over 2 pi omega naught, T to infinity, T prime, and which is alpha star. Okay, so now we have two solutions, and if they are the same, remove the camp. If they are the same, and we are saying exactly the same, then it should all work out. We should be able to show that it is the same. And 3 minutes. Oh, I don't even have 3 minutes. Negative 6 minutes, 6 seconds. Okay. So let me at least write that down, and I'm just going to, okay, I'll at least put it as an exercise for this. Yeah, and then we will, just that part will come and do that. Okay. Just write the solution. Yeah. If you allow me. So x of p now is, the new solution is alpha. That's more what is it? Yeah, let me come back and do this. because we will have the video, right? I'll at least just, okay, next time I'm not going to do the whole thing. I'm just going to start from the solution. Start from the solution here and show that it is indeed the same. And we will then, I want to do a couple of more examples on Friday, so it might be a little faster maybe. This shows up in electrostatics. Maybe if you give me 1 minute, let's say, if you have a positive charge, this is the axis X and Y, and I have a comma 0. I have a positive charge here. What is my potential at point here, X, Y, Z? 0. What is the potential there? So it will be Q over 4 pi epsilon naught times 1 over, that's my R, minus of A I, right? Isn't that correct? That's my observation point. That's my source point. 1 over R is your potential. Now let us say I keep a mirror here, literally a mirror. What's the difference between a mirror and a conductor? Huh?
To get a same charge.
Yeah, but what is the difference between a mirror and a conductor in the physical sense?
Conductor gives negative charge.
I agree, but what's the difference between a mirror and a conductor in the physical sense? When I look at a mirror,
Like same,
huh?
I see same image. But,
I see an image of myself. So if I look at a conductor, will I see an image of myself?
also,
Mirror is a conductor. Mirror is a glass, but glass is just a substrate. It is coated. So mirror, this is glass, right? That's the glass. It is coated by silver at the back. All the effects that we see is with the metal. In the olden days, they polished metal. Metal is very expensive, right? They don't want so much of metal. So they use glass and then spray metal on it. This is silver usually. Like they spray metal, so save metal because metal is more expensive. But for all purposes, mirror is metal. We are looking at the properties of a metal, right? So I keep a mirror here at the axis, put a positive charge, again ask what is the electric potential there, and let's assume that it's a perfect metal. Like for our most basic digits, it is really a perfect metal for our purposes. Then what is the observation point? Remarkably, this is what you probably studied in electromagnetism. You can forget the mirror and put a negative charge. This is called method of images. Minus A00. This is nothing but minus Q over 4 pi epsilon naught. And R plus AI hat. Okay, these are called method of images. You probably studied this in electromagnetism. We will do this as either as a homework problem on Friday. I will introduce this to a certain extent. Okay, I should stop. Thank you for extra 5 minutes and getting it hacked. Oh, so now if it is truly grounded, that's what happens. It has to be grounded only then it happens. If you don't ground it, then it's an added voltage there. Yeah, you're correct. No, so the point is if it is grounded, there is sufficient charge it can pull up. And it will pull the charges in such a way that there are negative charges here, more negative charges here, less negative, more negative charges. If you put a voltage there, you constrain that, then that disturbs everything. But still, what we are going to do, method of images, is when it is grounded. Otherwise, it is just a constant that is coming out, but still it changes the charge distribution everywhere. We will keep it simple. Electrodynamics will keep it but good point. A good observation. Yes. Oh, Niranjan is still, yeah, Niranjan is still here. Oh, I did keep the, yeah, okay. Yeah, thanks.
Thank you,
Suresh.
Dr. Rajesh, then.
Was
See
I
you next
better
time.
than, was I better than Aryan?
Oh, yeah, it was perfect
Ah, I
today.
was-
Oh, I thought that.
No.
See you the
No,
next time.
he did good. It's just, yeah, okay. Thanks, Niranjan. Okay, bye-bye.
See you the next time.
Now, if it helps, I do the same thing in the math potpourri and I struggle.
Yeah.
So it was not a complaint. Very good. Right. Listen, see you people, but thanks again. Hey, are you teaching now here? Where are you? Oh. Oh, you're teaching here now? Oh, meeting. I'll take just a couple of more minutes.
We
and-
don't have other papers.
Oh, so it's only Manuka? Okay. Yeah. Then I'll.
No, we have other people.
You want to end this
They're coming.
in the meeting?
Yes, please.